In Part B, we're asked to use the answer to Part A, which I have in purple above, to find the limit as x approaches 0 of 1 minus x squared minus f of x over x to the fourth. And so if f of x is e to the negative x squared, then basically what we're looking for in our numerator is 1 minus x squared minus that whole series there. And you can see that what happens when we do that is that the first purple 1 minus x squared is going to zero out with the black 1 minus x squared, and everything else is going to change signs. And then that's all going to be divided by x to the fourth. And finally we want the limit as x approaches 0. So if we were to simplify the remaining terms, you would get negative x to the fourth over 2 factorial x to the fourth plus x to the sixth over 3 factorial x to the fourth. And you can see the pattern beginning to emerge there. Alright, so let's simplify that one more time. And you're going to get negative 1 over 2 factorial plus x squared over 3 factorial minus x to the fourth over 4 factorial. And so what happens here, then as x approaches 0, all of those terms to the right of the first term are going to zero out, and you're going to end up with simply negative 1/2, since 2 factorial is 2. And so that's the answer to Part B. Again, pretty straightforward when you see the idea there. So we're going to go on to Part C. I'll scroll down. Part C says write the first 4 non-zero terms of the Taylor series for the integral from 0 to x of e to the negative t squared dt about x equals 0, and use the first 2 terms of your answer to estimate integral from 0 to 1/2 of e to the negative t squared dt. So if e to the negative x squared, you know, is this function here, or is this series here, what we're looking for is the integral from 0 to x, which is basically just saying we want the integral of e to the negative x squared. Recall that in any integral we're going to wind up with an x term, and so when we evaluate that at 0, where x is equal to 0, those should all go away, and we're just going to have basically the antiderivative of e to the negative x squared without any constant c. And so very simply we want the integral of each component, and the first term will be x, the second term will be x to the third over 3, negative. The fourth will be x to the 5 over 5 times 2 factorial, and that will be positive. The fourth will be negative x to the 6th, or at negative x to the 7th over 7 times 3 factorial, with and that term will be negative. Right, so those are the first 4 terms. Now we can't say that this integral actually equals that, but we can say that it is estimated by that, or we can do a plus dot dot dot, and that would tell us that that pattern continues on. Now we want to use the first 2 terms of that answer to estimate the integral from 0 to 1/2 of e to the negative t squared dt. And the first 2 terms are just x minus x cubed over 3. Now an interesting reason, another big reason why we use Taylor series and all, and Maclaurin series, is because this is a function, e to the negative x. I apologize. I wrote those incorrectly there. They should have been negative t squared, and I wrote negative x to the t. Alright, so fixing those. The point is that we have no way to find an antiderivative for e to the negative t squared. It can't be done using u substitution. And so because of that, using Taylor series and Maclaurin series is another way to algebraically evaluate functions. And because when I plug in 0, that the antiderivative evaluated at the lower limit will all wash away. So we just have to plug in 1/2 into those 2 terms above, and we get 1/2 minus 1/24, which is 12/24 minus 1/24, or 11/24. Now once again, it's important to note that we can't use the equal sign here because we are approximating, and it will take off points for that. And we should really do the same on the one above, since we're only using 4 terms instead